Live. Er zitten hier nog reservebatterijen in. Voor die speaker. Maar ik weet niet of dat nodig is. Ik weet niet wanneer dat ze het laatst vervangen zijn. Die batterij staat hier wel low. Anders vervang ik één en vervangen we één in het andere. Kijk, de microfoon in ook wel. Ah, en dat is effectief al beeld.
Ja.
Maar het is wel vertraagd.
Dus ja, want er staat nog niks op van.
Ja, daar ben ik.
Mag ik het precies?
Je hebt wat problemen met het set te staan, dat voor mij.
Ja. En nu begint het te komen op het.
Nu mag niet met het proberen met het set te staan. Hoe zou dat komen? Dat hij heel tijd.
Nu is het goed, ik heb, maar het is precies niet echt leesbaar.
Maar misschien moet hij nog zijn resolutie wat bufferen. Ja, ik hoor mezelf ook al babbelen, dus. Neem jij ook een schermopname voor de zekerheid?
Vorige keer heb ik dat niet gedaan, maar ik ben het vergeten.
Ik zou dat wel doen.
Maar
Want soms valt hij in het midden uit en dan is de schermopname wel handig.
yes. Ik was dat van plan de vorige keer, maar dat is wel een huisje zo.
Ja, ik vergeet dat ook soms. Je moet daar zodanig veel denken.
Ik kan dat nu wel aanzetten. Kan ik wel.
Ja.
Ik kan er dan aan knippen. Is het trouwens.
Kijk, die is normaal zijn bezig. En vandaar moest die uitvallen en die schermopname, kun je nog altijd die schermopname online zetten en dan... Hallo. Ja, voor mezelf duidelijk bouwen. Heb jij een sleutel van teamlokaal?
Yes.
Zet je hem na afloop terug in het teamlokaal? Dan moet je maar gewoon binnenrollen in het teamlokaal.
Ja, dat is de vorige keer ook.
Want
Dat is goed.
iedereen weet toch wat dat is. Dus. Dan zetten ze hem wel onder mijn bureau. Kan je niet op bed lopen.
Ja, maar ja, dat is nooit. Dat is wel werk genoeg.
Ja, het is dat. Dan ben ik door. Veel succes.
Ja, precies.
En veel plezier jullie. Geniet ervan.
Als zo in ons gezicht lachen zeg.
Het is nog een mooi uur, het is 5:15. Een beetje na 6 ben ik thuis. Succes weer.
Dat is onze nacht dus. En nu is het aan het regenen dus.
Is dat het erin?
Ja, het is al het is mijn elektrische bureau.
Maar dat kan. Lukt ook. Ja. Goed, salut. Bye.
Nee, ik ga nog zo. Dus hard je zelfde valsteken doet.
Er niet te hard in doen, dat is geen tafel. Sorry.
Yes, so let's start. Lecture 2 today. We're going to talk about database schemas, normalization, and we're going to learn how to use the MySQL workbench. So in our previous lesson we started off with what is actually a database. It's a collection of data that needs to be stored in a structured manner, and databases are used everywhere. We've seen how a database system is composed. We've seen the hardware part, the software part, and of course our data and our users are very important. And some characteristics of a good database system are sufficient storage space, it should be quick, it should have a little or no redundancy, it should be secure against non-users, and of course it should have a clear structure. In order to do so, we've used the database management system, which is basically a software application to use your database, to interact with your database, with other users, with other applications. And this is used to store, retrieve, manipulate your data, and it's also used to give certain users certain rights. And then we focused mainly on relational databases, and started with our relational database management system, MySQL, which enforces data integrity and referential integrity. So the MySQL, we've installed the server on our Linux system, and we've created a root user and our own user with certain privileges. We've created some databases, granted our user privileges to these databases, and then we started working with our recently created databases. In order to do so, we used the SQL language, which consists of three main parts: the data definition language, to create or design your database; the data manipulation language, which is used for the main part of your interaction with your database, so the CRUD interactions to create, read, update, and delete data in your database. And then we have the data control language, which is used to manage database rights. An SQL statement generally looks like this. So we have several clauses, and then inside these clauses you can have expressions or predicates, and it's basically read as normal language. In our MySQL database, we've encountered several column types, starting with an integer, so just a whole number. It can be signed or unsigned, and we have some more detailed integer values like tiny int, big int, or small int. In order to store numbers with a decimal point, we can use both float and double, depending on the number of digits after this decimal point. And then we can use a date in order to store a date. The default format is year, month, date, but of course you can change that as well in your MySQL. More in detail, we also have the date time, which just stores the date and the time, as the name says. And then one of the main column types, which is quite often used, are char or char. Both store strings or a certain amount of characters. The difference between char and varchar is mainly visible in storage space or the speed. If you want to store large parts of text or other data that does not need to be searchable, you can use a text or a blob for images. And if you know beforehand which values you will allow in a certain column, you can always use an enumeration. On top of these column types, we also have certain constraints, which we saw. So each table should have a primary key. There can only be one primary key per table, because all values must be unique. Keep in mind that a primary key can be one column or a combination of columns. We can also invoke the unique constraint on a column. This is to make sure that all values or a combination of values in these columns is unique, but it's not necessarily used on the primary key. Primary key is by default unique. You can also state that your column value or your field value cannot be null or not be empty. You can state a default value for your field, and you can use foreign keys. Foreign keys are used with our joins, which we saw. They're not obliged, but they speed up your join. And then we've seen some SQL queries, or insert query to insert data in our table, or select query to select or to retrieve data from our table. And then we've elaborated on these select queries with our order by. In order to sort our data, we use built-in functions on calculated rows. We've used column aliases. And then we started filtering our data with our where clause. We also touched the subject of null values. And in our where clause, we can also use Boolean logic to combine certain expressions with an AND or a NOT or an exclusive OR. In order to get the unique values out of our database, you can use distinct in a column. And to limit the number of result rows, you can use a limit function in combination with an offset or without the offset as well. And then we've looked at our aggregation, so we've filtered our results and we want to do something on those results. In order to do so, we used our group by in combination with the aggregation functions. Keep in mind that the columns you use in your select should be of a certain value based on your column which you group by. In order to filter the columns in the group by, we've used our having, so we can use both where and having in an aggregation function. And then our SQL statement will look like this. So the execution order will be that firstly our input columns are determined, then we filter them with our where, we sort and we group our filtered input with a group by, then we calculate our aggregation functions, for example a count or a minimum or maximum value of a certain column, and then we filter these aggregation functions with our having, and then we sort our output with order by, and we can also limit or chop the number of result rows with our limit. This is for a standard SQL query. And then we can make it even larger with our join, where we join two or more tables in our query. There's an inner join, a left join, and a right join. Keep in mind that the outer join does not exist in SQL. And in order to use these joins, or to speed up these joins, we use a foreign key, which is basically a primary key of another table. And this foreign key is used as an index. And then we saw different relationships between tables. We have a one-to-many relationship, where a result in a table can have many linked results in another table, or a many-to-many relationship, where one result in a table can have many results in another table, and vice versa. And this is only possible with our cross-reference table. And then, if our query is quite often used, instead of re-querying our database over and over again with an elaborate join, we can also create a view out of this query, and then this is stored in our memory as a temporary table. And then we can just do our select query on our view, and it's just on one table instead of on several tables with our join. Another way to speed up our queries is by using an index. Keep in mind that you can only use one index per query. And we also touched the subject of allowing a certain amount of redundancy based on our database systems. We have a snowflake and a star system, where in the snowflake system we don't allow any redundancy, which makes our system slower. Our star system does allow a certain amount of redundancy, and it's both faster, but it uses more storage space. And then we've ended up dumping our database or creating a backup of our database with MySQL dump commands. So this was the last time. In order to get reacquainted with the select status, I'll maybe do two exercises with you. And then I'll place the rest of the solutions online. So remember from last time, when we want to connect with our MySQL monitor, we used the MySQL keyword, and I will collect as root. I will ask for a password. And if you're connected, you can see that the MySQL keyword appears on the left side, and then you're inside of MySQL. We want to use the bioinf database, so we can first check our databases, show databases, and then we see all our databases which are available to us. So I will use the bioinf, so just type use bioinf. And then you can see it says database changed, and now we can start selecting inside our database. So we want to search for the accession number for the 3 longest human genes in the database. So genes will be in our gene column. If we want to show our columns or show tables, we can see our tables in our database. So we know that our database bioinf consists out of 4 tables: class, gene, gene view, and mod.org. Gene view is probably the view we created last time. So if we want to select the 3 longest human genes, we will start by selecting the accession number and the length of the gene from gene, and we will use an alias in order to reduce the amount of typing we have to do. But of course in genes, all our genes are in there, so not only our human genes. So we will have to join with our model organisms. And if you check your tables, so if you do a select star from your gene or from your mod.org table, you will see which columns are in there. And I know that I want to join them. And inside my gene table, so we can use the alias G, there is a column named mod.org ID, and this should be the same as, of course, the ID in the mod.org table. If we do this without any filtering, it will select these genes. So these are all the human genes with accession number and length that are inside our database, or all genes actually, because we didn't filter on human again yet. So if we want only the human genes, we need our genus to be and then we see that there are only 4 human genes in there. We want the top 3 or the 3 longest. So we will have to order them by length in a descending manner. So from large to small. And we only want the first 3, so limit 3. And this gives us the 3 longest human genes in the database with accession number and length. Alright, maybe just one more. So the last one we will do. So retrieve all unique class names for model organisms with at least 10 chromosomes. So we want all unique class names. Well, let's check our mod.org. Table. You can see that there's a class ID in there. So we will have to join this with our class table. Again, we do show tables. You can see that there's a class table as well. So I will select for now everything from our mod.org table. I will again use the alias MO. And I will join this table with our class table. And inside my mod.org table there was a column named class ID. So using the dot notation, mo.classID. This should be equal to the ID in the class table. And if I do this, I get an entire list of genes, which doesn't say much because right now it just shows the class ID inside the class table and this class ID, and it just joined them. We of course want only those with more than 10 chromosomes. So our number of chromosomes is in here. So filtering with our where the number of chromosomes should be at least 10, so 10 or more. So larger than equals 10. We're using a number, so no quotes needed. And we want the unique class names. So we can see here, other names aren't unique, because we have mammals 4 times. And in order to do so, we will change our column selection. Instead of selecting everything, we want a distinct, so unique, only the unique values of our name column. And if we do so, we now selected only the unique class names for the model organisms with at least 10 chromosomes. Right? So now that we're reacquainted with our SQL, we know how our MySQL monitor works, and it executes data definition or language commands. But of course, our MySQL monitor is only command line, so it's mostly used on servers for advanced users. For the basic user, there's a graphical user interface to interact with MySQL as well. And some graphical user interfaces are highly SQL or a MySQL Workbench. And we will work with MySQL Workbench. You can easily download the MySQL Workbench from their website. But it's even more easy if you just do it in your terminal. with these commands. Let me just copy them for you. So basically this is the URL you get if you click the download button on the website. You can copy it from there. So if you go to this website, maybe I should show you. You can always ask me later. And then we need the workbench. We want it for Fedora. Based on your version, you choose the 29 or 28. So let's say I installed the 28, for example. If I click the download button, it should bring me to this. And then, no thanks, just take it to download. If you click right here, copy the link, then you should have the link right here, and then you can just get it, and then just paste it. If you've done so, you can then install it with your yum. So just sudo yum install and then the name of the package you downloaded. So this should be the same name as the one you downloaded here. The MySQL Workbench is also available on Windows or on Mac OS. If you like to install it on another operating system. And once you install it, the MySQL Workbench will give you a nice and easy to use graphical user interface to interact with your databases. So once you've installed it and you open it, you will see this welcome screen. So welcome to MySQL Workbench, where you can, on your left-hand side, choose between three options. You choose the first one with the little dolphin. You can add connections to your MySQL server. When you start off, you will have no connections, so just click the plus sign to add a connection. Then this pop-up will appear. Choose a name for your connection. This can be any name you want. Just keep in mind that it should be one you can remember. So if you name all your connections localhost or localhost 1, localhost 2, it will be quite difficult. But for now, we only have one connection, so localhost is quite okay. Because our system is on our own computer, we will use the default settings, so standard TCP/IP, selected by default. Double check that your host name is localhost or the IP address of your local host. So this will be 127.0.0.1. We'll use the default port, so 3306. And then your username, you can connect either as root or as your own user. It's a good idea to keep two separate connections, one for your root user and one for your own user. But for now, let's start with our root user. So username is root, and then click test connection. It will prompt you for your password, enter your password, and if it says test OK, then you can save it, and then it will appear in the list right here. And then your MySQL Workbench will have one or more connections. If you then want to add another connection for your own user, you can follow the same principle, just change your username to your username you set, you selected the last lesson, and change your password. Again, test your connection and then save it. And if you now want to connect to our database, it's as easy as just double-clicking one of your saved connections. Again, it will prompt you for your password if you have chosen not to save it. You can save it in your password manager or in your keychain, depending on your operating system. Keep in mind that storing the root password is by default not such a good idea for your own user, maybe less harmful, but for your root user, do not store it. And then if you entered your password, you will see a screen something like this, maybe black or white, depending on your color scheme of your operating system. And then your screen looks like this. And on the left-hand side, you have a navigator pane. Again, depending on your version, you will have to click on schemas on top here. You will see the navigator pane. And in this navigator pane, you will have all your databases which are available to your current user. On the right-hand side, you have your query tab, where you can write your SQL code. So you can write all your statements or SQL queries in. If you executed a query, you have your results pane, which shows your results, if there are any of your. And at the bottom, you have your output pane, and it gives you an overview of your recent queries. And of course, there's an error message if your query fails. In practice, this will look like this. So if I, for example, select the database, let's say the bioinf test DB, to select it, just double-click your database. So the one in bold is the database that is currently active. So if I want to change my database to BioDB, just double-click it, and you'll see that this is now in bold. So if I want to do this for the bioinf test DB, I can check my tables. So I have exon, exon transcript, gene, and transcript. So let's say I want to select everything from exon, but of course I will limit this to 10 rows. And then I can just press the lightning bolt over here, and this will execute all my SQL statements written in my query. And then I can see my result pane, where it shows a table with all the result rows I asked for in my query. So now I've selected 10 random rows from my example table. At the bottom, in your results, on your output pane rather, you will see you can change between text history, text output, or action output. Well, action output is selected by default, and there you can see the query which you executed and the response. If it failed, the response will say fail or error with an error message. Alright, so as I mentioned, these are all your different databases on the server. If you have access to them, the bold one is the one currently selected, and you can browse your tables in your database here. And if you click a certain table, then you get more information on the currently selected item. So for example, in this database, I selected the gene table, and inside the gene table, I have several columns. I can check the column names with their column types and their constraints. Alright, so you can try it for yourself here or at home. And why do we use this MySQL workbench? Well, MySQL workbench is quite easy to work with certain data models. And what is a data model? Actually, well, it determines the structure of your data. So we have a conceptual data model, which is just where you state your structure of your entities and the relationships between these different entities. And this is stored in an entity relationship diagram. A MySQL workbench is able to create these kind of entity relationship diagrams for you. The second data model is the logical data model, which exists of the structure of the tables and the references between the tables. So relations and the foreign key constraints. And this is stored in a data structure diagram. And then we have the physical data model. And with physical we mean, of course, the manner on which data is stored. So are there partitions in your database? How many CPUs do you want? How many storage space do you need? And these three types of models you can find in database models. And the most simple database model is a flat model. It's just a single two-dimensional array of data elements, and the most known example of this is an Excel spreadsheet. So an Excel spreadsheet is actually a flat model database. And then we have the hierarchical model. And in this model, data is organized into a tree-like structure, meaning that each child record has only one parent, whereas each parent record can have multiple children. Inside these kinds of models, a record is a collection of fields, with each field containing only one value. And these fields are defined by an entity type. So as you can see, records are connected through links. A network model then is basically two tree models combined, where each record can have multiple parents as well as multiple child records. And then we have the relational model, which consists of tables, and these tables are relations. And the links between these tables are not explicitly defined, so we use keys. And this is basically what we've been using so far. So if we use our MySQL database and we've connected them through our joins, the links between our tables are actually the foreign keys. Another type of model is the object relational model. This is basically a relational model with object-oriented features, as the name states. And this is used in the PostgreSQL language. And then we have the object-oriented model, where data is represented in the form of objects, and they use the same model of representation as in the programming language. For example, NoSQL systems will work with these, but we will see those in the last lesson. So what do we need to keep in mind? Well, if we want to create our own database according to one of these models, or in our case, our relational model, we will need normalization. And normalization is just basically organizing columns and tables to reduce redundancy and to improve integrity. Remember, we've mentioned Colt in the first lesson, just briefly mentioned them, and he came up with some normalization rules which we will have to apply in order to create a new database. So basically, with normalization, we always start with the unnormalized form. And this is done by grouping all data into one entity. So every type of data you have, just group them into one entity. To go from the unnormalized form to the first normal form, so 1NF, we will have to eliminate all repeating or calculated groups into individual tables or individual relations. Then we will create a separate table for each set of related data. And in each of these data sets, we will identify a set of related primary key well. If we've done so, we can move on to the second normal form. And then we have to check for each of our relations in the 1NF that every non-prime attribute of the table, so every non-prime attribute in our relationship, is dependent on the entire key of every candidate. So meaning that if we have a data in our table, that a certain attribute is dependent on the key attributes in the same table. If we want to progress to our third normal form, we will have to check for every relationship in our second normal form that every non-prime attribute is non-transitively dependent on every key. Meaning that every attribute that is not part of a key does not depend on another non-key attribute. And then we have the Boycott normal form, where any attribute on which some other attributes are fully functional dependent should be a determinant. And every determinant is a candidate key. So meaning that none of your keys can contain information on any other key inside the same table except about the entire primary key. And then you still have the fourth normal form, the essential tuple normal form, fifth normal form, sixth normal form, and the domain key normal form. Basically, if you can normalize up to third normal form or Boycott normal form, you will already have a quite good database. So how does this look in practice? Well, say we get a table with some data. And we have to normalize this in order to create a database. So we know that we will have to start with our unnormalized form. So in our unnormalized form, we just put all data into one entity. So we create an entity, we give it a name, in this case DB, but the name doesn't matter, and then we store every attribute or every data point in our relationship. So patient number, patient name, appointment number or appointment ID, our time, and our doctor. Alright? If we want to go to the first normal form, we want to make sure that each attribute has a single value. This is the case. If it's not the case, we want to eliminate the repeating or the calculated groups and create a separate table for each set of related data. So we have no repeating groups in this table because each of our attributes has only one value. So our first normal form, in this case, will look exactly the same as our unnormalized form. Only difference is we will indicate our candidate keys. So in this case, we will use patient number and appointment number as candidate keys because based on these attributes, we will be able to retrieve the other ones. And then for our second normal form, we have to make sure that every non-prime attribute of the table is dependent on the entire key of every candidate key. So basically, we will have to check if patient name is dependent on both of these or on one of these. And if this is not the case, we will have to split up our relationship. So in our case, patient name does not rely on the appointment number, for example. So our second normal form will look like this. We have split up our relation into two relations. We still have our first relation with our patient number or appointment number or time and our doctor, because time and doctor are dependent on the combination of these, but our patient name is only dependent on our patient number. So this needs to be stored in a different relation. Alright? If we then want to progress to our third normal form, we will have to check that every non-prime attribute is non-transitively dependent on every key. So meaning that if we check our normal forms, that every attribute that is not part of a key, check every attribute that is not part of our key, so every non-prime attribute is not dependent on another non-key attribute. So in our case, we'll have to check for each of these relations if a non-key attribute is dependent on another non-key attribute. Well, is doctor dependent on our time? If we check our data points, no, because for the same time point we have a different doctor. Is time dependent on doctor? Well, no, because a doctor does not see his patients on one single hour. So meaning that for the first relation, this is okay. For the second relation, we have to check if the non-key attributes are dependent on another non-key attribute. Well, there is only one non-key attribute, so this is okay as well. So meaning that both our relations are in third normal form. So our entire relation or database is in a third normal form. So basically, our third normal form is the same as our second normal form. And then we will have to check if, for our Boyce-Codd normal form, if every attribute on which some other attribute is fully functional dependent is a determinant, and every determinant should be a candidate key. And if we do so for our relations, so these relations, we will see that our doctor is dependent on our patient number and our time. Our second relation with patient number and patient name just stays the same. And our appointment number is actually dependent on our time. Because we'll see that if you go before noon, you have a first time slot, a second time slot. If you go in the afternoon, you will have a first time slot and a second time slot. Alright? This is quite abstract, of course, but this is necessary in order to create a good database.
Appointment numbers, dat je het eerste game, dus die database, de appointment numbers niet eruit halen. Zodat die volgende, die patient number?
Yes. So here, it's still in there because we've selected this as a candidate key. But if we check our functional dependencies, and we will see that this is no longer the case, because actually our appointment number is not our key because it's dependent on our time. Going back to our data, if you go, like I mentioned, before noon, and we will start appointment ID 0 will be the patient that comes at 9 with this doctor or this doctor. If you come at 10, you will get appointment ID 1. If you come at 11, you will get appointment ID 2, and so on and so on. If you come after lunch break, then you will get, again, if you're in the first time slot, appointment ID 0. If you're in the second time slot, appointment ID 1, and so on and so on. So meaning that appointment number is actually dependent on our time slot. Alright? Maybe a second example. So again, we get some data. So why would this table not be in the first normal form? Well, we remember that for a relation to be, or a table to be in the first normal form, every attribute should have a single value. Well, this is not the case. As you can clearly see, telephone numbers has for certain rows more than one value. So in this case, telephone number is a repeating group. So in order to get this relation in the first normal form, we will have to normalize this, and it will look something like this. So if we check our unnormalized form, we will name our relation branch, for example. We have 3 columns: branch number, branch address, and telephone numbers. So this is just getting all our data points into one relationship. If we then want to progress to the first normal form, we know that there are repeating groups. So again, we start with our main relation. Branch number, branch address can be in there as well. But telephone numbers was our repeating group. So we will have to create a new relation for our telephone numbers. But we of course want to link this to our other data as well. So for example, we will call this branch telephone. And in this we store our branch number again and our telephone number. Alright? If we then want to go to our second normal form, going back to our definition stating that second normal form, that every non-prime attribute of our table is dependent on the entire key. So meaning that every non-key attribute is fully functionally dependent on the key. In our case, we know that our branch address depends on our branch number, because if we have the branch number, then we can retrieve the branch address. So our first relation is in the second normal form. For our second relation, branch number and telephone number, branch number is again our candidate key, and telephone number is dependent on our branch number as well. So meaning that our second relation is also in the second normal form. So we can state that our second normal form is the same as our first normal form. For our third normal form, we will have to check that every attribute that is not part of our key cannot be dependent on another attribute that is not part of our key. Well, in our case, it's quite easy. If we do this for each of our relationships, we only have one non-key attribute, branch address, so it cannot be dependent on another non-key attribute. So our first relation is already in 3NF, and for branch telephone, we also have just one non-key attribute, telephone number, so it cannot be dependent on another non-key attribute. So again, this relation is already in 3NF. So this makes it quite easy for us, because our 3NF is actually the same as our 2NF for this example. Alright, and if you want to identify all keys, as I mentioned, branch number will be our key in these relationships. right? So if we then want to do this on another table with a bit more data, we'll see that this kind of data, for example, of a veterinary. And we have several columns in our data, so pet ID, pet name, pet type, pet age, owner, and then a visit date and a procedure. If we would place these in our unnormalized form, we'll just call it pet, for example. So we have our pet ID, pet name, pet type, pet age, our owner, and then if we check our example, visit date and procedure, this combination is actually a repeating group, because this type of data representation is basically the same as in our previous example, where we have 3 telephone numbers in one column. You can write this as 3 visits, for example, in one column as well. So this is one value, second value for the visit, and a third one. So this is a repeating group. We can write it with extra brackets if you want, so visit date, procedure number, and procedure name. As you can see, I already split those up, procedure number and procedure name. Because these, we'll use this as procedure number and this as procedure name. Become clear why I've done so in our normalization. So now we've just grouped all our data into one entity. In our first normal form, we need to split the repeating groups in different or in separate relations. So we'll keep our first relation with our info about our pet. And then, as I mentioned, we have some information about the visit. But we still need to link it to our pet, of course, so we store the pet ID in here as well. We have our visit date, our procedure number, and our procedure name. Alright? Still clear? So in order to progress to our second normal form, we again, if we take our definition with us, we'll have to make sure that all non-prime attributes or non-key attributes are fully functionally dependent on the entire key. So in our case, for our first relation, let's check our data table. For our first relation, we will see our key is pet ID, well, all the other information, pet name, pet type, pet age, and the owner are dependent on the entire key. So we can just copy this for our second normal form. And our first relation is already in the second normal form. Then we will check our second relation, our pet visit. And if we can see from our table that a single procedure can occur on multiple dates, we will have to include our visit date as part of the key. Alright, so our key in this relation will be pet ID visit date. So we'll have to check if procedure number and procedure name are dependent on the entire key. Is this the case? Well, for pet visit, we still have pet ID and visit date, of course. But then we can already appreciate that our procedure name will be dependent on something else, on a procedure number, of course. So we will have to create a new relationship with our procedure data. And if we then check our third normal form for each relation, we'll see that the first one is already in the third normal form because these are our non-key attributes, but they're not dependent on each other, so the pet type does not depend on the name you give your pet, or the owner does not depend on the name you give it, and so on. Same goes for our second relation. Only non-key attribute is procedure number, so it cannot be dependent on another non-key attribute. And for our third relationship, the only non-key attribute is procedure name, so it cannot be dependent on another non-key attribute. So again, this relation is as well in the third normal form, so stating that our third normal form is basically the same as our second. As you can appreciate from these examples, sometimes or most of the times with these quite straightforward examples, some of the normalization or most of the normalization is already done in 1 or 2 steps. Alright, I'll leave the last exercise for you to do, or the last 2 for you to do at home, maybe, or maybe one more, because this is another type of exercise. So let's say you get your data already in relationships, so not in a table this time, and you have to check your normal form, and if it's not normalized or not normalized enough, you have to progress your normalization steps. So let's say this or these are our relations, and these are our functional dependencies you will get. Based on these type of data or type of results, we will have to check on which normal form the data is. So firstly we check, are there any repeating groups? To check if it's in the first normal form or not. Well, we can't see any repeating groups, so we can state that our relationship, or each of our relationships, is in the first normal form, so our entire database is in the first normal form. Right? Then, for our second normal form, we have to check if each non-key attribute is dependent on the entire key. Well, for our first relation, our director is dependent on our title, because a movie or a video just has one director. Our serial number is again dependent on our title. So our first relation is in the second normal form. For our customer relation, we'll have to do the same. Our key is member number. Name is dependent on member number, because based on the member number we can retrieve our name. Same goes for address. Address is dependent on your member number as well. So the customer relation is in the second normal form as well. It's a bit more tricky for our higher relation, because we have a composite key. So now we have to check if we can find member number with just serial or just date. Well, this is the key. If we check our functional dependencies, member number is found with the combination of serial and date, or is dependent on serial and date, this combination. So we can state that member number is in our third relation, is fully and functionally dependent on the entire key. So again, this third relationship is in the second normal form as well. Is it in the third normal form? Well, let's check. In the third normal form, we have to check if the non-key attributes, if there are non-key attributes which are dependent on other non-key attributes. And we can immediately see that in our first relationship we have two non-key attributes, director and serial. And if we check our functional dependencies, you can see that director is dependent on serial. So meaning that the first relationship here is not in the third. And we can already stop here, because we know that if one of our relations is not in a certain normal form, then the entire relation or database is not in this normal form. So at this point, this database is in the second normal form. In order to convert this to the voice code normal form, we'll first have to go from second normal form to third normal form. So we know that our second normal form looks like this, because it's given to us. So we have a video relation with the title, director, and serial. We have a customer relation with name, address, and member number. And we have a higher relation with member number, serial, and date. And we know that from our functional dependencies, we know that director is dependent on serial. So we will have to split this. So our video relation will look like this. Title, serial. Title still being our key. Then we have a serial relation, where serial is our key. And director. Our customer relation you'll have to check if this is the third normal form. So we'll have to check if there are non-key attributes that are dependent on other non-key attributes. Check our functional dependencies. So name and address. Is one of these dependent on each other? Well, no. You can see here, so the combination name, address, member number depends on that. and vice versa. So we can state that our customer relationship is already in the third normative form. So name, address, and member number. And then for our higher relationship, we can do the same. Serial and date is our key there, and we know from our functional dependencies that member number is dependent on those. But since member number is the only non-key attribute, it cannot be dependent on another non-key attribute in the same relation. So this stays the same as well. And then, moving on to our Boycott normal form, we will have to check if every determinant is a candidate key. So, in our first relation, title, serial, if we check our functional dependencies, you can see it over here. Title is dependent on serial. So, this is already okay. Boycott normal form. And then our second one is serial. So there our determinants are serial. And if we check our functional dependencies, you can see that serial director is in there. So serial is a candidate key. So again, we can state that this relation is in Boycott normal form. Then our customer relation, if we check those, we can see that we have those two, and they are both candidate keys, member number and name address. So again, making this quite easy. No alterations needed. Customer relation is in a Boycott normal form. And then we apply the same principle for our higher relation, where we have just one candidate key based on this functional dependency, serial date, member number. So again, our determinant is a candidate key. So higher is as well in the Boycott normal form. So therefore, our entire database is in Boycott normal form. All right. So as you can see, before you start creating your database, some normalization is needed, but this is quite abstract if you don't know how your database will look like. And that is why some database types do not need normalization. Unfortunately, relational databases do so. Will seem quite hard now, but if you do some exercises on this, it will become more clear. And then going back to our MySQL workbench for a more fun part, of course. If we've done the normalization, we can start creating our tables. And if we go back to the MySQL workbench, and you click the home icon, so far we've used our connections, but we can also create models in the model interface. And this is the second part in MySQL workbench. If you click on there, you can see models. So far I've saved none, but in the same fashion as we created new connections, you can also create new models. And what does this do? Well, it's basically creating tables. So if you click the plus sign, you can start with creating a new database model. So click the plus sign and then add a new diagram. Just double click it and then you will get something like this. And this is basically just your plain worksheet where you can place tables with just one click of the mouse. So I will add a new diagram. This is my worksheet. Just hover over these to check where your tables are. I think it's this one. Place a new table. Yes, and then just place it. And you will see I've created a table in my database. It's easy as this. Of course, this table does not have a suitable name and does not contain anything. So in order to modify this table, just double click it and a new page will pop up where you can change the name for your table and you can start adding columns. This will look something like this. So place your table, double click it, and then start editing it. And if we look more in detail, this edit pane on the bottom, so here will look like this. So we have our name for our table, our column names, and then we can start modifying our columns. So you choose your column name, first column preferentially an ID column, so just ID, make it an integer, make it primary key, so PK stands for primary key. If you click this, normally the not null constraint should be checked by default, because a primary key cannot be null, because MySQL uses this to identify the rows. You can choose an unsigned integer if you want to do so, but maybe more handy will be the auto increment, stating that if you use a number for your key, MySQL will automatically increment the last value or the last known value for your key with 1. So auto generating a new key. And then some other columns, first name, last name, can be varchar. Specify the length of your varchar, or the max length. Specify if it can be null or not null. So first name can be null in this table. Last name cannot be null, so we have to fill in a last name. And then date of birth with just the date type and no further constraints. And you will see immediately that the table you placed on top on your worksheet will have changed. And now these columns you've just created will be included in your database or in your table. If you then create a new table, just place it somewhere else on your workbench or worksheet, add some columns as well, and then we can start by linking these tables. If you've created a column, now we are working in the columns tab, but at the bottom you also have a foreign keys tab, and this is used to add the foreign keys to a certain table. Alright, we'll make an exercise on this in just a moment. So basically, just give your foreign key a name, this can be anything, then choose your reference table from a drop-down list, choose the column in your table, and choose the reference column in the other, in the reference table. If you've done so, you will see that based on your constraints, of course, these selections are, options are limited, and then a line will appear between your two tables. If you hover over this line, it will highlight two columns in the tables on which they are. Let's skip this for now. So if we want to create a database scheme that looks like this, we start off with our students table. So table 1 will be students. Go back to our columns and we will start adding columns. So we'll have a student number. This will be an integer and our primary key. Cannot be null. We will not use an auto increment for now. Name will be a varchar. Last name. Keep in mind that your column names cannot contain spaces and that they are, or that MySQL is case sensitive. So meaning that capital letters and small letters do not mean the same. Birth date will be a date, so you can just select it, go through the list, select date, this can be an enumeration, or we'll state, for example, male, female. Keep in mind that when you are specifying your enumeration options, if you're using strings, they should be between quotes. If you don't do it correctly, the type will disappear again and it will change back to varchar. And then our last column, trajectory ID. And this will be an integer as well, and it cannot be null. Alright, so if we check our worksheet, we can still access it. You can see that my students table is created with the columns I specified. It has certain indexes, but just ignore these for now. And then I will place a new table and start from there. So the second table I will create is, for example, the trajectories table. Start adding columns as well. So an ID column, which is primary key and not null, and a trajectory. Can be the Alright, so now I've created two columns and I want to link them together. So then I will have to go to my foreign key tab on the bottom. And we'll just choose a name. It can be anything. I have to make sure that I need the correct table. So my foreign key will be in my students table, so I'll have to select my students table. Go to my foreign key. For my reference table, so now I'm in my students table, I will choose my trajectories table. And then on the right hand side, you can already see, these are my columns in my student table. I want to link them on trajectory ID. And then I can see I can only choose two columns, and by default the ID in my trajectories column is selected. Why is this? Because they have the same column type and the same constraints. So they are both integers and they are not null. And then it's okay. No further actions needed. And as you can see, there's a line between my two tables. And if I hover over it, it clearly marks the two columns that are linked in my database. As you can see in your tables, if there's a key next to it, it's a primary key. If it's just a red button, then it means that this is a foreign key. A white one is just a normal column. So you can just move those around. And then we need a third column, or table, which will be our courses. I have an ID column over there. Again, primary key, and it cannot be null. Then I have my course name. Let's state this as a bar chart as well, do not change it, and how many credits I get for this. Let's change this to an integer of 2 digits, for example. So now I can get credits from 0 up to 10 for this course, or up to 99 actually. Alright? So now, as you can see from our exercise, the courses and the students table are linked in a many-to-many relationship. This was a one-to-many relationship, this is a many-to-many relationship, because a student can follow multiple courses, but a course can be followed by multiple students, of course. So, in order to join these, we will need a cross-reference table. We will name this course of student, or student in course, as you please. And this will just contain a primary key with no meaning, and then 2 foreign keys, student ID and course ID, which link to our separate tables. So if you go back to your model, you can now create your last column. This will be the course of student. Again, an ID column. And I have my student ID. This should be an integer as well, because I want to link it to the primary key in my students table, which is an integer and is not null. The same for my course ID. Also an integer, cannot be null. And now I want to set my primary keys, or my foreign keys rather. So I switch back to my foreign key tab at the bottom. I want to link it to my students table, and I want to link my student ID, so I select the student ID, and it automatically selects my student number in my students table. I can double check if it should not be another column, but no, student number is okay. So this is already okay, and then I can add a second foreign key. I want to reference my courses table based on my course ID, and of course this is linked to the ID in the course table. Alright? And if I then check my model, I can see that both links or foreign keys are added. So I have 2 foreign keys in my cross-reference table, which link out to the student number and the ID in it. So now we've created the same model or database sheet as we've seen in our previous lesson. Of course, so far we only have this model, but not our database. But in MySQL Workbench, we can forward engineer this model to create a database. This is quite easy. So, before you start, just make sure you've changed your database name to a name you prefer. So by default, I will choose MyDB. You can just call it students or something like this. Just close it. Like this. So now you can see that the name is changed to students. And then on top in your menu there should be, mine has disappeared. So in your menu there should be a function. So if you click database and then forward engineer, and then just follow the wizard, it should, let me just check database. Okay. It's just not on the screen. So database forward engineer, and then it will look something like this. So you have your model, and then this will pop up. Now we can start forward engineering. So we will choose a connection. So basically stating to our MySQL Workbench, use this connection to create our new database. So choose one you stored. Probably you stored only one, so your local host. You don't have to change anything, and then just click continue. This you can just skip. So do not change anything, continue, and then it already prompts you for your password. If you did not store it in your keychain, go OK. And then it says export MySQL table objects, which is checked. We have 4 total objects. You can just show your filter. You can see that we will create our students database, and we have 4 tables in there: course of student, courses, student, and trajectories. If you want to do so, you can include or exclude these tables. Now they are all included. If I want to exclude them all, I can just use this, include them all, or just select the one and say I don't want this table. But for now, of course, we want all tables. We did not create any views or any other objects, so these should not be checked because they're empty anyway. Just click continue, and then you get a bunch of MySQL code in order to review the SQL script if you would like to do so. But let's just presume that MySQL or you did not make any errors in creating your model. You can always save this to a file, so maybe for now let's do so. So let's call this students.sql, and then I have my SQL file if I want to import this database. Like so. Remember from the previous lessons or from the exercises that you had to import a .sql file in order to create a database. Well, this is such a SQL file. Only now this SQL file does not contain any data, just a structure for your database. And then if you are satisfied with it, you can also copy it to your clipboard if you would like to use it, but just click continue. Again, it will prompt you for your password. Just click OK. And then if everything was successful, you see a bunch of green icons over here, and it should state forward engineering finished successfully. You can just close it then, and then go back to your connection. So if you close it, go back to your home and reconnect here with your stored connection. If it's still open, just go there. And then on the top, you can see a refresh over here. Just click it. And then you should see that your newly created database should be in the list of databases. As easy as this. So now we've created a new database entirely in our graphical user interface, just placing our column or tables and entering our column. Of course, this database does not contain any data. So if you'd like to insert data, you can also just use your insert command. So insert into and then the name of the table. So for example, students. Then state your columns here, and then values, and then in the same order as you stated your columns, just give your values for your columns. All right. Yeah, so in your menu, which is hidden for some reason here on this screen, so you have several options, and it's database and then forward engineering.
So when you like file edits, like query, and like in normal.
Alright, so now we found an easy way to create new databases. Instead of just typing the entire SQL code yourself, you can just do it graphically and then let MySQL Workbench create the SQL code for you. This is an exercise for you to do at home.
Should we only be able to do it in the graphical user interface or also?
You can choose.
What for the exam?
For the exam, I don't think we will have enough time to do it manually, but if you are quicker manually, you can always do it manually, but most of the time a graphical user interface is used because it's way quicker than typing everything. So of course, before you start creating your database, you'll have to, there are some important questions. Firstly, which data would you like to store? What are the constraints on my data? For which application will I use this data? So will I allow redundancy or not? Because based on certain applications will need to have fast retrieval of the results. For others it's not that important. And what are the relations between my data? And all these questions are answered in our entity relationship diagram. Next to our forward engineer, we also have a reverse engineer, where we can start from a database that already exists and create a model out of it. So if we go back to our database view or connection view, you can reverse engineer it by clicking database reverse engineer. So I'll have to do like this again, database reverse engineer. And then this pops up. Again, choose your connection, continue, you'll ask for your password immediately because we will have to retrieve your databases. Now, select the database you want to reverse engineer, for example, the bioinf test DB. Just click continue. Again, a bunch of green icons if it finished successfully, and then continue. you can see again which objects will be imported. So we know from our connection view that the bioif test debate has 4 columns. We want to include them all, so just keep it like that and then execute. And then it created a nice model for you, like so. Maybe we should move these around. Like this. And then you can check all your tables in your database. So now we can appreciate from this model that it's basically quite similar to our students model we created just now. So there's a one-to-many relationship between transcript and gene. And there's a many-to-many relationship between transcript and exon. And exon transcript is here our cross-reference data. Alright? So you can again check your keys by hovering over observations, or you can select your database or table and just check the foreign key and the primary key in. Alright, so forward engineering is to go from a model to a database. Reverse engineering is to go from a database to a model. And then MySQL Workbench also allows you to export data. So remember, at the end of the previous lesson, we did a dump with the MySQL dump command in order to dump the entire database. MySQL Workbench allows you to export a certain part of your results or an entire database as well. So going back to our connection part, so if we, for example, here, so I selected 10 random exons from my database, and then over here you have the export import function. If you want to export your results, you can just click the export thing and then just save it somewhere. You can choose your format. It can be a CSV or a JSON or whatever you want, depending on the application you want to use it for. You can also dump your entire database, but this is hidden somewhere in the menu. And then only an export is available, but an import as well. So next to our export button, there's an import button, and you can import either an entire dump file or data from your file you just created with your export. So this can be any of the types you used for your export. You can import as well. So let's say I would truncate a table and then choose import. You can just browse for your tables. For example, I have here some data from the mod.org table. So I can immediately fill it with my export data, if you do so. And this means we can now start not only querying an existing database, but we can also create our own databases. So we started off with our database schemes. We then normalized our data in several steps. And then based on these normalization, we can start by creating our tables. You can choose to do so in your MySQL monitor, or a bit more easy in your graphical user interface using the MySQL workbench. By just placing your tables on a worksheet and then forward engineering your model, you end up with an entire database. And then only thing that remains is filling the database with data. And we've seen in the previous lesson that you can use the insert command for this. Alright? Keep in mind that you should be able to normalize a database yourself, or normalize data yourself in order to create a database. You should be able to create a database model in your MySQL workbench, and you should be able to create a database with your workbench or with just plain SQL statements, whichever way you prefer. Alright, only tip I can give you is for the normalization, just try the exercise over and over again. It will seem quite abstract for now, but if you do several of them, it will become more clear. And once you're an advanced normalizer, you will see that you can sometimes just create a database which is already normalized without you even noticing it. Any questions? No? So in the next lesson, we will end up with our NoSQL systems, meaning so far we've seen our SQL systems, our relational databases, which use the SQL language or statements. But now we will progress to the NoSQL systems, which to the joy of most of you don't need any normalization. We will also see some online databases, and then we'll advance through APIs and version control, and APIs meaning publicly available databases which are retrievable to other ways than just a plain connection with the database. Alright? A bit shorter, but that was it for today.